Hello everybody. Today we're going to start a new chapter. We previously previous chapter we study only resistor component. Now we proceed to two more components which are capacitor and inductor. Capacitor and inductor are termed energy storage element. In this chapter, two energy storage elements, namely capacitor and inductor, shall be studied. We will study the wireless connection of capacitor and inductor, including current voltage analysis and energy storage of the element. Capacitor. The diagram in figure 5.1 shows the basic constructor of parallel plate capacitor. A capacitor consists of two conductors separated by an insulator called dielectric. One form of capacitor, which is parallel plate capacitor, is shown in figure 5.1. If the voltage between the two plates is V, and then capacitance is C, then the charge and voltage capacitance just in the capacitor is given by Q over CV. We mean that the charge equals to where C is the capacitance, which is a measure of amount of charge stored in the capacitor. The larger the value of capacitance C, the greater will be the amount of Q that can be stored for given voltage V. For this figure 5.1, the capacitor relation is given in C permittivity A over D, where this symbol is given by, is called the permittivity of the dielectric material. A is the plate area, D is the separation between the plate. We start with capacitor connected in series and parallel. Figure 5.3 shows capacitor connected in series. For capacitor connected in series in this plate with the three capacitor connected in series, the total charge QT equal to sum of charge of Q1, Q2, and Q3. The total charge QT equal to sum of this one, Q1 plus Q2 plus Q3. Applying Kirchhoff voltage law, the voltage source E is equal to sum of voltage drop across C1, C2, C3. So apply KVL, Kirchhoff voltage law, E equals to V1 plus V2 plus V3. So given by this one, E equals to V1 plus V2 plus V3. So substitute Q equal to CV, then E equals to, E is the total, E is the total voltage, so equals to, this is equal to QT over CT, is the total charge equals to total capacitance, equals to C1 is given by Q1 from the equation, Q1 divided by C1, then V2 is equal to Q2 divided by C2, then V3 equal to Q3 divided by C3. Knowing that total charge is QT, total, since the current series capacitor current remain the same, so the current is the same in this circuit. So QT equals to Q1 equals to Q2 equals to Q3 equals to Q. So this whole thing become, this QT also Q, this part Q, This part become Q, this one become Q. So dividing both sides of the equation, both sides of this equation by Q, the total capacitance is equal to 1 over CT equal to 1 over C1 plus 1 over C2 plus 1 over C3. This is C3. So this for capacitor connected in series, like this one, like this. So in this diagram 5.3, the total capacitance, equivalent capacitance is equal given by equation, given by this equation. Okay. Then for capacitor connected in parallel as shown by this circuit, for capacitor connected in parallel, the voltage across each capacitor should be the same. For capacitor connected in parallel, since the capacitor connected in parallel, the voltage across each capacitor should be the same. Mean the same as E here. So current flow to here into branch 1, branch 2, branch 3. So current is this current is equal to sum of these 3 branch current. So the total charge is equal to sum of charge of capacitor Q1, Q2, Q3, QT equal to Q1, Q2, and Q3. Because of that, because of the current, total current flow to here is split into 3 branches according to Kirchhoff current law. So and then it combine back to become QT, I total. So Q total equals to Q1 plus Q2 plus Q3. So substitute the value Q equal to CV, QT equal to CT E supply energy, supply voltage. Then Q1 equal to C1 V1, C2 Q2 equal to C2 V2. Then Q3 equal to C3 V3. Say since E equals to V1 equals to V2 equals to V3, because of the parallel connection of this 3 capacitor, and then whole thing is connected across E. So E equal to V1 equal to V2 equal to V3. Let's substitute to this equation E V1, substitute E to here. So this can be then the total capacitance eliminated all the V term, voltage term. So the total capacitance for parallel is equal to C1 plus C2 plus C3. So this for capacitor connected in parallel, 3 capacitor connected in parallel as shown in this figure. Then this one is the equation for total capacitance connected in series as shown in this figure. Then capacitor current and voltage. When the capacitor in this case, capacitor charging circuit. Initially, capacitor is what? It's empty, 0. Assume capacitor empty. It's connected to a resistor R. So when capacitors close the switch, so the voltage across capacitor VC will rise exponentially until after roughly 5 times constant, it becomes steady state, stable at E, this value E, same as the charge. This capacitor voltage, final steady state is charged to this voltage E. And so in this curve, initially capacitor is empty, then when switch close, it starts charging until steady state E. This part of the curve is called transient interval. Transient interval. Then this part of the curve is called steady state. Then this charging equation, this charging process of VC voltage VC again, time can be can be given by this equation. VC equals to E1 minus exponent minus T RC, where RC is what? RC is these two values, these two, R and C. Okay? It's called, RC is called what? RC is defined as time constant, Then the current, this current IC is what? Current IC, this current IC. This current IC is given by this one. It's given this equation, is IC here, charging current. It's given by what? It's given by this equation, E divided by R exponent minus T over tau. This tau is equal to RC. Okay? Then this IC, this VC, capacitor voltage, is equal to this equation. Capacitor charging current is equal to this equation. Then the shape of the curve is this one. Switch close, current maximum, and then after charging until capacitor nearly full, it become become dropping until 5 tau, it becomes 0. Then the resistor voltage is what? VR. VR is this one. VR is this one. VR is this one. So VR is given by this one. Okay? So when this VC, we analyze the curve here, this curve, according to this equation, this is tau. One tau means that this is tau here, RC tau. For 1 tau substitute to here, this after this get this get what percentage is? 1 tau substitute to the equation is 63.2%. Then 2 tau substitute to here is how much? It's roughly equals to 86.5. Then 3 tau, 4 tau, 5 tau. After 5 tau, it becomes 99.3%. Same, this is IC and VC. For this IC, VC, that be the same curve. Same, substitute the tau to here, to this part, substitute tau to this part, it becomes dropping. And then after 5 tau, it nearly 0, stable, steady state already, nearly 0, fully charged capacitor. Okay? So this example, we will discuss during our full lecture time. I will discuss with you this example. Then capacitor discharging, charge, and then after fully charged, first capacitor in this position is what? Is fully charged. Capacitor close, this switch close is position 1, is switch in position 1, the capacitor charged to what? Voltage E, charging by current IC. When it's after 5 tau, long time after capacitor fully charged, switch to 2. Become here 2, capacitor will what? Fully charged, then it will what? Discharging through R, same R. Through R, okay? Through R, through resistor R, discharge. Then capacitor discharge equation. Capacitor VC for discharging, this discharging for VC, discharging is equals to this one. VC equals to E exponent minus T RC. RC is what? RC is the tau, same as this one. Same as this R and this C. And this C, okay? Then VR for discharge, VR. This one, VR. It's become minus sign. Minus E exponent T tau RC. Similarly, IC. This IC. direction is reverse to charging current. Charging current reverse. So the value will be what? The equation will be minus E over R exponent minus T RC. This discharging capacitor discharging. Discharging. Okay, discharging. So this is capacitor, discharge voltage, steady state fully charged, then discharge. Discharging become 5 tau, it cannot be 0. Then capacitor, charging current, discharging current, first maximum is maximum in minus E over R, then discharge. Because smaller and smaller, and then 5 tau becomes smaller. Okay. Then example 5.3 discuss in full. We will discuss in full lecture. Next, we cover capacitor with charging and discharging with initial condition. Means that usually this part got initial condition with initial condition. Before that, we study all with what? All with empty, no, zero initial condition. Now we study with what? Initial. We want to cover with what? With initial condition. Then the equation is given by, for the capacitor is given by what? It's given by this one. Given by this one, 5.14. Okay? Okay, this one easier. Then for example 5.4, we will cover during full lecture. The energy stored in capacitor is given by what? W equal to half CV square. Half CV square. Energy stored by capacitor. Then example 5.5, we will do in what? Lecture. Full lecture. 5.6 the same, we will do in full lecture. Then inductor. The inductor is a coil. It's made from made from wire with number of n turn and number of coil, and it can be wire on core material such as iron or air. So with this inductor symbol, if we enter construction, the symbol in here is here. This is air core with a material is iron is double line. So voltage induced in capacitor, this voltage will be equal to V over L. L is inductor value, di dt. V equal to L di dt. It's voltage across inductor. Then the L is given like this L is given like n square. N is number of turn here, n square. This n square. This n square. Then mu permeability. Mu is what? Permeability. Mu is permeability. A is the area. This area. This area. Then length. Length is this part. This one. This is the length. Okay. So energy stored in inductor is E equal to half Li square. E equal to energy stored in inductor is half Li square. Inductor store energy in magnetic field. Capacitor store energy in electric charge. So inductor connected in series. Inductor connected in series like this. Their equivalent, total equivalent is equal to sum of L1, sum of individual. Just add. L equivalent total is L1 plus L2, L3 until Ln. Okay. Then inductor connected in parallel. Like this, connected in parallel. Connected in parallel like this. Connected in parallel L1, L2, L3 until Ln is equal to 1 over L equivalent equal to 1 over L1 plus 1 over L2 plus 1 over L3 plus 1 over L4. Okay. So example 5.7 we'll cover in full lecture. After finishing this lecture, we will do tutorial 5 like this. We will do tutorial in the tutorial session. Okay. So okay, thank you for listening. Thank you for listening.